Hey everyone, and welcome. Today we're going to dive deep into the world of line and angle relationships. We'll start with something you literally see every single day, perpendicular lines, and use them as a launch pad to explore some really core ideas in both geometry and the world of logic. So let's get right into it.
So, here's what we've got on top. First, we're going to pin down exactly what it means for lines to be perpendicular. Then, we're going to do something super cool, a step-by-step logical proof. From there, we'll zoom out and see how this one idea fits into a much bigger concept in math called relations. And finally, we'll see how all these rules let us build things with perfect, guaranteed precision.
Before we jump into all the definitions and symbols, just take a second and look around you. Really look. The corner of the room you're in, the screen you're watching this on, even how a tree trunk meets the ground, it is all geometry. The ideas we're about to break down, they're not just stuck in a textbook. They are the invisible blueprint for the world we live in.
All right, let's start at the beginning. We all have this gut feeling, right? We know what perpendicular looks like. But here's the thing about math. A gut feeling isn't nearly enough. We need a definition that is absolutely rock solid, something we can build our entire logical case on.
When somebody says perpendicular, this is probably what pops into your head, isn't it? A perfect cross. One line going straight up and down, and the other going straight left to right. And that's a fantastic starting point, because it's such a crystal clear example.
Okay, now for the official, formal definition. Perpendicular lines are two lines that meet to form congruent, adjacent angles. Now, those two words are key. Congruent just means they have the exact same measure. And adjacent means they're right next to each other, sharing a side. So basically, all four angles that get created when the lines cross are all equal.
And this picture shows a really important point. Perpendicular lines don't have to be perfectly flat and upright. They can be tilted, they can be rotated any which way. What really matters is that 90-degree relationship between them. And anytime you see this little square symbol tucked into a corner, that's the universal sign that says, hey, these two lines are perpendicular. Okay, now this is where things get really fun. In geometry, we can't just look at something and say, yeah, that looks like a right angle. We have to prove it using nothing but pure logic. We're about to build an argument step by step where every single statement is backed up by an unbreakable reason. This right here is our goal, to prove this theorem. Now, it seems kind of obvious, right? If lines are perpendicular, of course they make right angles. But proving why it's true, without a shadow of a doubt, is what gives mathematics its incredible power.
So let's set the stage. We are given one fact, and one fact only. Line AB is perpendicular to line CD. Our mission, should we choose to accept it, is to use that single piece of information to prove, logically, that angle AEC is a right angle, which means it has to measure exactly 90 degrees.
All right, let's start the proof. Step 1 is always the easiest. We just state what we already know to be true. Line AB is perpendicular to line CD. And the reason? Well, it was given to us. Simple. Now, for step 2, we have to ask ourselves, what does that perpendicular symbol actually mean? Well, we just defined it. It means the lines form congruent adjacent angles, so we can logically state that angle AEC is congruent to the angle right next door, angle CEB.
Okay, let's keep building on that. In step 3, we're basically translating from geometry speak into algebra. If two angles are congruent, it just means their measures are equal. So now we have an equation. The measure of angle AEC equals the measure of angle CEB. For step 4, take another look at the diagram. See how angles AEC and CEB sit together on that straight line AEB? Well, one of the fundamental rules of geometry is that a straight line, or a straight angle, always measures 180 degrees.
And now we start connecting the pieces. Step 5 uses something called the angle addition postulate, which is a really fancy way of saying that part plus part equals the whole. The little angle AEC plus the little angle CEB adds up to the whole big angle AEB. And now for the magic of step 6, substitution. We know from step 4 that angle AEB is 180 degrees, so we can just swap out M angle AEB in our equation and put 180 degrees in its place.
We are so close. Look at the equation we have from step 6. We can simplify it even more using substitution again. Just look back to step 3. We already proved that the measures of AEC and CEB are equal. So we can replace M angle CEB with another M angle AEC. Now our equation says 2 times the measure of angle AEC equals 180. From here, it's just simple algebra. Divide both sides by 2, and bam! Step 8, the measure of angle AEC is 90 degrees.
And for the grand finale, we just state our conclusion. Since we've proven the measure of angle AEC is 90 degrees, we can officially conclude that it is, by definition, a right angle. Proof complete. Sometimes you'll see QED at the end of a proof. It's Latin, and it basically means, we did it! We showed what we set out to show. Pretty cool, right?
So we just spent all that time working with the relationship is perpendicular to. Now I want to ask you to pull the camera way back with me, and let's talk about what a relation itself actually means in the big wide world of mathematics. This is where we go from concrete to abstract, and it's incredibly powerful.
So let's just think about this. What are these phrases we use all the time, like is perpendicular to, or is equal to, or is greater than? What are they actually doing? On the surface, they seem totally different, but they're all playing the same fundamental role in logic.
They are all what mathematicians call relations. And a relation is really just a rule that connects two objects. It's that simple. Look at this table. Is equal to is a relation that connects numbers. Is perpendicular to connects lines. But it's not just a math thing. Is a brother of is a relation that connects people. The concept is absolutely universal.
Okay, now that we know what relations are, we can start to look at how they behave. Because not all relations are created equal. Some follow very specific rules, and we can actually classify them based on 3 key properties.
These are the big 3, the reflexive, symmetric, and transitive properties. And they're just ways of describing how objects in a relation behave, with themselves, with a partner, and in a chain. So let's take a look at each one.
First up is the reflexive property. For a relation to be reflexive, an object has to be able to relate to itself. Think about it. Any number A is always equal to itself, right? So the relation is equal to is reflexive. But can a line be perpendicular to itself? No, that doesn't make any sense. So is perpendicular to is not a reflexive relation.
Next up is the symmetric property. Think of this one as a two-way street. If A is related to B, does B have to be related to A? And this is a perfect fit for what we've been talking about. If line L is perpendicular to line M, does that automatically mean that line M is perpendicular to line L? Yeah, of course it does. So is perpendicular to is a symmetric relation.
And last, we have the transitive property. This is like a logical chain reaction. If A relates to B, and B then relates to C, does A automatically have to relate to C? If it does, the relation is transitive. For example, if angle 1 is congruent to angle 2, and angle 2 is congruent to angle 3, then you know for a fact that angle 1 must be congruent to angle 3. So congruence is transitive.
Okay, let's bring this all the way back to our perpendicular lines. All these abstract rules and logical proofs, they have very real, very practical consequences. They lead to theorems that guarantee we can build things in the world with absolute certainty.
So why does all this matter? Because it leads to these incredibly powerful theorems. Theorem 1.4.3 tells us that at any point on a line, there is exactly one line that can be perpendicular to it. Not 2, not 3, just 1. And Theorem 1.4.4 says the exact same thing about a perpendicular bisector. It's unique. This guarantee of uniqueness isn't just a neat math fact. It's the foundation that makes things like precision engineering, architecture, and even computer chip design possible.
So, let's end with the question for you to think about. We've seen how these properties create order in the world of geometry, but where else do they pop up? Think about it. Social networks, family trees, computer programs. Where else do these fundamental rules of logic, like symmetry and transitivity, create the predictable structures that we all rely on every single day?